All right, let's get started. This will be up shortly. Okay, so a few notes about what's going on in the class. So the milestone report was due already, and hopefully all of you have turned it in. And then we'll have instructions for the feedback. So we'll be doing feedback from other students, again through CMT, and we'll give you instructions for how to do that today probably. So keep an eye out for that. We'll post that on Piazza. And then homework 5 is out. Sorry about the delay. So we've moved back the due date so that you get the same number of weeks to do homework 5. And homework 5 is a little different than the rest. It's kind of a choose your own adventure style homework where you have a few choices about what to actually do. So you can use that to explore one of the advanced topics, whichever one you're more intrigued by. You're welcome to do more than one, but we'll only grade one of them. I believe there's also an extra credit portion there, so you can check out the assignment for the details about that. You can do all 3 if you want. And then this is a little bit further away, but I wanted to put it up here now so that you guys can plan for it. So if you look on the course schedule, you'll notice that the last 2 lectures are actually blocked out for final project presentations. So those last 2 lectures concretely are on November 28th and November 30th. So those will be the days for the final project presentations. They'll be very, very short presentations because there are quite a few students in the class. So each of you will probably have maybe like a 2-minute slot. And it's mainly just meant for you to be able to present the main results of your final project. The final project report is due during finals week after that on December 12th. So you will have a bit of time, almost 2 weeks between your presentation and the actual final project report, and you can use that time to finalize your project. So even though these are the final project presentations, they might not be completely final, and you will have an opportunity to get a little bit of feedback there as well. So the final reports will be due on December 12th. Okay, so where are we at in the course so far? We had the first half of the course which dealt with reinforcement learning algorithms, and there we learned about model-free reinforcement learning, model-based reinforcement learning, and also a little bit of imitation learning. Then we had a second part of the course which dealt with advanced topics: exploration, inverse RL, variational inference, meta-learning, multitask learning, and so forth. And starting next week, we'll enter into the third and final part of the course where we'll actually have research talks and guest lectures on cutting-edge topics in reinforcement learning. So we'll have 4 excellent guest lectures for you to cover more advanced topics, and that will also hopefully give you a little bit more inspiration as you go into the final stage of finishing your final projects. And today what we'll do as a transition is we're not actually going to talk about any new algorithms or anything like that. Today we're going to talk about some big challenges and open problems in reinforcement learning. So I'll tell you a little bit about what I think are big challenges and open problems and things that maybe could be tackled in future research. So that's really the purpose of today's lecture. But before we get into that, I do want to talk a little bit about the guest lectures that we'll have starting next week. So next Wednesday on November 7th, we'll have a talk from Craig Boutillier from Google Research, and Craig will talk about his work, and his work concerns with theoretical questions in reinforcement learning as well as reinforcement learning algorithms for things like recommender systems and systems that interact with end users, typically over the web. So, you know, there was a little bit of a robotics emphasis to this course because my research is in robotics, and I often make robotics examples, so I wanted to specifically get some guest lectures that deal with other areas where reinforcement learning can be applied. So Craig will hopefully cover some of that. On Friday, Craig Gregory-Kahn, who's a GSI in the course, will talk about his research, and his research concerns mobile robots and collision avoidance, as well as hybridization of model-based and model-free techniques. Then on Wednesday, November 14th, we'll have a talk by Kwok Lei from Google, and Kwok works most recently on reinforcement learning and stochastic search algorithms for architecture search for neural networks. So this is another very different application area for reinforcement learning algorithms, and those of you that are interested in architecture search, as well as things that involve large-scale compute and so on, this is a really excellent lecture to check out. And then on November 16th, we'll have a talk from Carol Hausman, who works on multitask learning, meta-learning, and robotics. So please do attend the guest lectures. Please attend them in person so you can actually ask questions. And we're actually going to ask the speakers to stick around afterwards for a little Q&A period So for those that are on Wednesday, that'll actually be during my office hours, so they'll just come with us to office hours. And if you want to ask some questions, you can come by and have a more informal discussion. They'll be around for a while, and I'm sure there'll be plenty of opportunities for interaction. And then for the speakers that are speaking on Friday, we'll try to set aside an additional time also for Q&A. So do make sure if you're interested in some of these topics, maybe you want to check out their website, if you have something you want to discuss with them or some questions to ask, something that pertains to your final project, for example, you can ask them those questions and you'll have plenty of opportunities to do that. Okay, so let's move on to the main topic for today's lecture. Today we're going to talk about the challenges in deep reinforcement learning, the kinds of open questions and the kind of problems that we're faced with and the kind of problems that we might want to try to tackle in future research. And these problems will range from the very mundane issues with optimization and stability to kind of more conceptual issues. So what's the problem? What are the problems? These are the particular problems that I think are quite important and that I want to discuss in a bit more detail today. First, there are challenges with the core reinforcement learning algorithms. So if we accept for a minute that the reinforcement learning problem is the problem that we want to tackle, trying to tackle that problem with the algorithms we learn about in this course often confronts us with a number of issues. One big issue here is stability. So does your algorithm actually converge? If you go and implement Q-learning, go and implement policy gradient, you run that thing, will it find a good solution consistently? Or will it find a good solution only one in every 100 runs? And there are issues here and there are things we can do. Efficiency. If it does find a good solution, how long does it take to find it? Does it take it a number of samples that is completely impractical to use in the real world? Does it take it a number of samples that requires you to run the whole thing on a giant cluster? This kind of stuff. And there are, of course, a lot more problems to be solved there, a lot more that we can do. And lastly, generalization. After it does converge, does it actually generalize effectively? And this is something that we often overlook, especially when we work on benchmark problems in reinforcement learning, but typically, viewed from a very high-level standpoint, if you're using machine learning to solve some problem, it's probably because you would like the solution to generalize to new instances of that problem other than the ones that it was trained on. That's what generalization refers to. So I'll talk a little bit about generalization in reinforcement learning. But besides challenges with the core algorithms, there are also some challenges that I think are worth dealing with in regard to the core assumptions. So reinforcement learning methods make a particular set of assumptions about how a decision-making problem should be structured computationally. And those are not the only assumptions that we can make. So is it even the right problem formulation? Perhaps we can formulate decision-making problems in a slightly different way. Perhaps we can change up some part of the problem statement, and maybe that will be a better fit for our particular task that we want to address, or it'll lead to solutions that are much more practical if we just change the assumptions a little bit. And at a very fundamental level, what is the right source of supervision for reinforcement learning algorithms? So any machine learning system, any machine learning method derives supervision from something. A supervised learning algorithm derives supervision from someone telling it the labels. A reinforcement learning algorithm derives conventionally supervision from a reward signal or a reward function. But there are perhaps other sources of supervision, other ways that we can look at this and think where is the source of information that the system is learning, and perhaps there are some things we can change about our assumptions to reveal to us more informative sources of supervision, or perhaps avoid requiring unreasonable sources of supervision that we might not have in reality. So we'll discuss that a little bit. But let's start with the challenges and open problems for core algorithms. And one big one that I'll begin with is discussing stability. So stability is, of course, very closely related to something that many of you are probably familiar with from having done the homeworks, which is adjusting your hyperparameters. So when I say stable or stability here, what I mean is you run your algorithm on a new problem, and the algorithm, maybe it doesn't give you a great solution, but it converges, it doesn't blow up and give you complete garbage. And to a lesser degree, stability is often used colloquially to refer to algorithms that are relatively insensitive to the choice of hyperparameters, meaning that you perhaps don't have to choose the learning rate just right. Maybe if you're off by a factor of 2 up or down, the thing will still do something reasonable. It's worth mentioning before I get into this discussion that in deep learning in general, even supervised deep learning, stability and sensitivity to hyperparameters used to be extremely severe problems. In fact, it used to be when things were first getting started in this field, maybe like 10, 12 years ago, you basically had to have done a PhD in one of 3 labs in the world that actually worked on deep learning in order to know how to set up neural network training properly. Now, since then, we've come a long way. The standard supervised learning algorithms have matured, and there are well-understood techniques that can stabilize supervised learning with deep nets and make it much more practical. But with reinforcement learning, we're arguably still in the world where regular deep learning was at 10 years ago, where it takes a lot of care and a lot of practice, and also some degree of art to figure out how to set up reinforcement learning algorithms for complex problems in a way that they actually converge and yield a good solution. So, of course, one big thing there is adjusting the hyperparameters of your algorithm properly. And there are challenges in this regard for every class of methods that we've covered, and I'll talk about each of them in turn. So first, let me talk about Q-learning and value function estimation methods. So methods that basically try to learn a value function for your problem. So here there is a conceptual, a theoretical issue, which is that many of these fitted value or fitted Q value algorithms with nonlinear deep neural network function approximators are typically not contractions. So even though the Bellman backup is a contraction, as we learned, composing the Bellman backup with a projection onto a function class is not a contraction, which means that there are no guarantees of convergence. So if you remember from the lecture in the first half of the course, this picture that if you apply the Bellman backup to your current value function, you move closer to the optimal value function in terms of the infinity norm, and when you then update your function approximator, you move closer in terms of the L2 norm, which is a projection, but composing these two may actually lead you further away from the optimal solution. So this is a theoretical problem, but this theoretical problem also shows up as a practical problem when we try to implement and use these methods. And in practice, the way that we mitigate this problem is with careful setup of hyperparameters. So the kind of parameters that might matter for value function approximation methods are things like the use of their target network and the delay between the target network and the current network, how much data you keep, which is the replay buffer size, some very esoteric points in regard to the setup of the gradient, like gradient clipping. Many of you probably set up the Huber loss for homework 3. The Huber loss actually ends up corresponding very closely to using an L2 loss, but with gradient clipping. So there's a close relationship there that you can look up, and that's why that was one of the things that you could try for homework 3. And then also just very basic stuff like sensitivity to learning rates and so on. Typically, when we do value function estimation or Q-learning, we use optimizers with some sort of adaptive learning rate these days, like Atom or something like that. You could also use SGD with momentum, but the less adaptive optimizers often take more care, more hyperparameter tuning, including learning rate tuning, to get them to work well. And partly that's due to the sensitivity of these methods to hyperparameters. We also have policy gradient methods that don't have this issue, but policy gradient methods have their own issues. So policy gradient methods use a very high variance gradient estimator. In fact, when we discussed model-free algorithms, the reason that we went over to Q-learning and value function estimation was because it actually drastically reduces the variance of the gradient. So policy gradient methods that do not make use of bootstrapped value functions have a high variance gradient estimator. What that means is that you need lots of samples in order to get the gradients to be sufficiently coherent to actually climb the reward landscape. And you need to make use of a variety of variance reduction tricks, things like baselines. And you can go very, very deep with designing better and better baselines to reduce the variance of policy gradient algorithms. But of course, that introduces complexity and oftentimes additional hyperparameters. So the kind of parameters that we have to deal with for policy gradient are things like batch sizes, learning rates, the design of your baseline, even very esoteric things like, for example, we didn't cover it in detail in this course, but when you design your baseline, you could actually take into account the fact that you're solving a finite horizon problem. We often don't do that. You didn't do that in homework 2, but you could take that into account. You can say, okay, I know my hopper needs to hop for 1,000 steps, so my baseline needs to be different at time step 999 than at time step 1, and that will actually improve performance. But all these little details actually end up mattering a lot, and they can be a little sensitive and delicate to set up, even though, in principle, policy gradient methods are guaranteed to converge to a local optimum. And then, of course, we talked about model-based reinforcement learning algorithms. And model-based reinforcement learning algorithms, in some sense, it's sort of a more diverse class of methods because there are many different ways to set up models, many different ways to set up planners, but they also have their own problems. So first, there are some very delicate decisions to be made in terms of the choice of your model class and how you fit that model, and also how you actually use that model to make decisions. And these choices they have very substantial ramifications on how well the method works, and they're often somewhat task-specific, somewhat domain-specific. So beyond that, there's numerical issues. Optimizing a policy with respect to the model can be highly non-trivial because you're essentially propagating gradients through a long temporal chain. And we discussed a bunch of tricks to try to get around that, but in the end, this is a basic computational problem, and no method avoids that problem completely. And then the more subtle but also very important issue is that model-based reinforcement learning is fundamentally a very adversarial process. You have this model that is trying to solve one problem, it's trying to basically produce a good estimate of realistic outcomes, and you have a policy which is trying to solve a very different problem. It's trying to actually send actions to this model that will cause the model to output high reward states. And these two processes can be adversarial because if the model can make a mistake and output a high reward state that is not a state that would actually be reached, the policy will find and exploit that flaw. So it'll find the flaws in the model that cause it to be too optimistic. And as a result, we have to deal with things like the policy overfitting to the model, we have to deal with uncertainty and so on, and this was discussed in the advanced model-based RL portion of the course. So this issue can be a very substantial issue. Okay, so let's talk a little bit about some of the things that we can do. We'll start with very mundane, very practical things, and then we'll talk about some more kind of researchy directions. So the very mundane thing is we have to get used to tuning hyperparameters. So maybe in some bright and distant future, this issue will go away, and we'll have wonderful AutoML systems that tune our hyperparameters for us on giant clusters that operate for free and don't cost lots of money. But until then, we have to get used to doing this ourselves. So, for example, one of the things that we can do very practically is to get used to writing our code in such a way that it makes it easy for us to experiment with many different hyperparameter values. Maybe if you expect certain things in your code to be hyperparameters that will require lots of adjustment, set up the code in such a way that you can easily run multiple values, maybe multiple values in parallel on a cloud compute service or something like that. One very pragmatic thing is to set up your code so that in some outer loop you can pass in big arrays of possible hyperparameter values and just have the thing try many values automatically. But one thing to keep in mind there is that the most natural way to set up big hyperparameter sweeps, at least for me the most natural way to do it, is to define arrays of possible values for every hyperparameter and then run all the permutations. But of course this adds up very, very quickly. So if I want, let's say, 5 different learning rates, 5 different target network update rates, and maybe like 5 different neural net architectures, okay, that I can maybe do, it'll take a while, but then if I want 5 more values of another parameter, 5 more values of another parameter, and so on, it becomes exponential in the number of parameters that I'm defining, and it's very expensive to run those kinds of sweeps. Not only is it expensive, it's actually a little pointless. There are better ways to set up hyperparameter sweeps when you have a large number of parameters, where you actually learn more from every run than you would if you used a grid layout. So a random layout is a little less intuitive, but it's generally more optimal. And it's basically the only viable option when you have many different hyperparameters that you want to adjust simultaneously. So to understand why the random layout is actually more optimal, it helps to look at a picture. This is a picture that I actually borrowed from a talk by Yoshua Bengio. And this is an example of a setting where you have 2 hyperparameters. One of them is shown on the horizontal axis and one on the vertical axis. And here it just so happens that the vertical hyperparameter, the one with the yellow landscape here, is just not as important. So maybe the green hyperparameter, maybe this is your learning rate, and you happen to be using an algorithm that is very sensitive to learning rate. And the yellow one, maybe this is your target network update frequency. So the target network update frequency is also important, but you can usually go up or down by 1 order of magnitude without the whole thing blowing up. So maybe this one is less important. It has less of an effect on performance as you vary it. Just 2 hyperparameters. I'm going to do a grid sweep with 3 values of each one. And that's denoted by these dots in the middle, so 9 total runs. The trouble here is that because this vertical hyperparameter is so unimportant, this point, and this point all yield essentially the same results. So even though I ran the algorithm 9 times, I only sort of learned 3 runs worth of information. So the only differences I got were this column, and this column. So I only really got 3 things. And I actually missed the really nice learning rate that would have achieved really good results because I only had 3 learning rates I was trying and just skipped right over the good one. So this is bad. If I had instead arranged my runs randomly, then I would have gotten much denser sampling on this important hyperparameter, I would have also seen many values of the unimportant hyperparameter and ignore them because they're unimportant. So same exact number of runs, but I would have actually learned a lot more. So here I wouldn't have missed this very nice value of the learning rate that actually achieves good performance. And of course, this is a 2D example where it wouldn't have been so hard to tile the space more densely, maybe use 5 learning rates instead of 3. But as the number of hyperparameters increases, the inefficiency from the grid layout also increases, and the random sampling of the parameter values can be a much better idea. That said, if you go that route, it's a good idea to spend a little bit of time thinking about what the right visualization tools for you are in order to actually understand what all these runs are doing. So it's easy to just take the best one and say, okay, I've just found the best one. But if you're developing algorithms, you also want to understand something about how sensitive your method is to different hyperparameters. And in that case, you might actually want to visualize the results from all the runs to try to understand how to improve your method in the future. And of course, don't forget about the random seed. Almost all reinforcement learning algorithms that we use are randomized algorithms, which means that they will produce different results when you run them with different random seeds. If you run them on GPU, if you use some sort of parallelism framework, they'll also produce different results depending on arbitrary factors like the time of day, the temperature in the room, how overheated your GPU is, and so on and so on. So these methods will be rather inconsistent. And keep that in mind. So make sure to run things multiple times to get an accurate estimate for how well your method is doing. And actually, in some sense, if you're running your algorithm in a reproducible setup where same random seed actually produces the same result if you use it twice, that can actually be, in some sense, a curse, because then it's very easy, if you get a little bit careless, to essentially overfit to your random seed. You run with the same random seed 5 times, adjust the learning rate. You don't know if you actually found the best learning rate or the best learning rate for that random seed. So be careful with this. And it's good to get into the practice of running multiple random seeds. Of course, that can be costly. That can slow down the iteration cycle. So perhaps one practical thing to do is to occasionally run with more random seeds. So maybe you try 3 random seeds every time you change your algorithm, and then when you go home for the night, run it overnight with like 10 random seeds, so that when you come back in the morning, you solidify the conclusions from your experimentation of the previous day. So reinforcement learning is self-reinforcing, which means that it's very likely to get into local optima. And different random seeds will fall into different local optima, and therefore you'll actually see very different performance. As a concrete anecdote that many of you might relate to, if you remember the half-cheetah task from the homeworks, the half-cheetah task actually has 2 solutions for effective forward running gates. One solution where the cheetah runs, and another solution where the cheetah flips over and runs on its back. The second solution is a little bit less efficient energetically, but it's still a pretty good solution. And depending on which of those modes your algorithm is falling into, you actually see 2 modes if you visualize the results from many different runs. So don't assume that it works well until you test a few random seeds. And we're actually going to look at a little example to illustrate some of the danger of this. Before we do that, the one quick warning. Keep in mind that the random seed is not actually a hyperparameter. So you do get different performance with respect to different random seeds. You can optimize over the random seed that just corresponds to a different kind of algorithm. It corresponds to a stochastic search over a random seed followed by RL. It's a legitimate algorithm. It's just you have to then say that, well, your sample complexity is each run times the number of seeds you've tried. But if you want lessons from algorithm development that actually extend to other problems other than the single problem you're testing this on, then don't treat that as a hyperparameter. You have to treat it as something that your algorithm is robust to. So let's do this little cute exercise. In this exercise, what I did is, I actually didn't do this. This was done by a student named Peter Henderson at McGill. And what Peter did is he experimented with, in this case, 2 different methods. And he was actually diligent. He ran each method for 5 random seeds. And then he plotted the mean and the standard deviation of the expected reward. And this is on the half-cheetah task. And then he wants to conclude, is the orange algorithm better than the blue algorithm? So let's do a little poll. How many of you think that the blue algorithm is better? Raise your hand. How many of you think that the orange algorithm is better? And how many of you think that they're about the same? Okay, nobody. So clearly it seems like the orange one is better. The error bars actually separate the 2, so that's, as a quick rule of thumb, it seems like a good cue. But it turns out that here, what Peter Henderson actually did is he ran the same algorithm, in this case trust region policy optimization, with two different groups of 5 random seeds. And the orange one shows the average over 5 runs with the first 5 random seeds, and the blue one shows the average over 5 runs with the second group of random seeds. And incidentally, the half cheetah does have these two modes. It has an upside down mode and a right side up mode, and it could just be that one of those groups of seeds had more of the upside down runs, which resulted in a lower average. So this kind of stuff can happen, and this is, in this case maybe it was unavoidable. 5 runs was quite a lot, and he just got unlucky. But in general, do keep in mind that you will pick up on spurious patterns that aren't actually there if you use fewer random seeds and you aren't very careful in checking things. Okay, hyperparameters. Any questions about hyperparameters? All right. So the reasons that this is a challenge, they're actually fairly obvious. You can't run your hyperparameter sweeps in the real world, so it would be really nice if you can develop algorithms that are robust to the choice of hyperparameters, because then reinforcement learning can be applied more broadly. It can be applied to settings where you cannot simply fire off multiple jobs on a cluster and come back in the morning with the results, but settings where you actually are learning from real data, where you can really only afford a small number of runs. And then you could tune your algorithm in the simulator. You can adjust your hyperparameters in the simulator, but then of course the problem is your simulator needs to be fairly representative. And sometimes the learning rate that works best in simulation will work best on real problems, but sometimes it won't. You could say that the hyperparameter sweep is part of your algorithm, which is actually a very reasonable thing to say, but then of course your sample complexity is equal to the number of times that you need to run the algorithm to tune the hyperparameters times the efficiency of the algorithm itself. So you're essentially multiplying the sample cost by the number of times that the algorithm is run, which sometimes maybe is a good thing because you might probably get a much better solution, but it comes at a steep price. So in effect, this makes your method be a stochastic search followed by gradient-based optimization, which is not a bad method. It's just a much more expensive method. So perhaps we can also develop more stable algorithms that are less sensitive to hyperparameters. And this is, I think, a very important, very open area of future research. So what can we do? Well, one thing we can do is we can take a more theoretical approach. We can study algorithms that have more favorable improvement or convergence properties. Perhaps we can study algorithms where we can prove under certain circumstances that these algorithms will improve with each iteration. Usually it's too much to ask that a stochastic algorithm in a non-convex setting can find a global optimum. That's very unlikely to be feasible. But perhaps we can devise algorithms that have favorable properties under more restrictive assumptions, which at least provide us with a signpost that researching further in this direction will eventually yield methods that have those kind of properties in realistic settings. And there are some examples of papers that do analyze convergence or improvement properties. For example, trust region policy optimization actually provides an improvement guarantee, but that guarantee is theoretically only valid for fairly small step sizes. So in practice, usually with this algorithm we use step sizes that are much bigger, but at least that result suggests that further research along this line might yield algorithms with more favorable improvement properties. There's also been quite a bit of work on safe reinforcement learning or high confidence reinforcement learning, where you can actually construct a sort of statistical significance test to say that if you used a certain amount of data and your algorithm estimates an improvement of a certain amount, then there is a bounded probability that it actually improved by a lot less than that. So if you say, okay, with probability no worse than delta, you improved by at least epsilon, then that's something that you can actually use in practice. You can say, maybe if you're using your policy to choose advertisements on a website, you can turn that guarantee into a guarantee on dollars. You can say, with at least this probability, I will lose no more than this number of dollars. And that's something that you can work with. You can look at algorithms that adaptively adjust their own parameters, so algorithms that don't necessarily require you to choose the parameters in advance, but will actually monitor how the learning is progressing and adjust the parameters as they go. One example, this is just an example, not by any means the only paper that does this, but one example is the QProp paper by Gu et al., which looks at adjusting a parameter inside the baseline for a policy gradient algorithm based on how much that baseline actually correlates with the actual returns of the policy. You want baselines that correlate with the returns because then your variance goes down. So what this method does is it actually reduces the multiplier if the correlation is low, forcing it to rely more on Monte Carlo estimates and less on the baseline. But of course, a lot more research is needed here. And perhaps research into algorithms that are more stable might not be so great for beating the benchmarks. It's not necessarily going to give you a better score if you tune the parameters just right, but having algorithms that are more stable is really essential to make reinforcement learning a viable tool for real-world problems. So there is a challenge in this regard as far as evaluation. How do you prove that your algorithm is more stable? Well, you have to run many hyperparameters, you have to analyze stability and so on, which is of course a little bit more onerous than simply reporting benchmark results for the best parameter value, but this kind of research is tremendously important to advance the field and to make reinforcement learning a practical tool. Let's talk about sample complexity. So this is the second point as far as core challenges with reinforcement learning algorithms. I went through this slide a while back at the conclusion of the model-based RL section, but I want to go through it again. And this slide is going to summarize the relative sample complexities of different algorithms. We're going to start at the top with the methods that require the largest number of samples, and end at the bottom with the methods that require the least samples. Keep in mind that the sample complexity isn't the only metric that matters, so I don't mean to imply that the methods at the top are bad and the methods at the bottom are good. It's just that some require more samples than others. But let's go through this and see how the different methods stack up. So at the very top, we have a class of methods that we didn't really cover in this course, but these are stochastic search gradient-free methods. So these are methods that adjust the parameters of your network, not using gradients, but just by randomly perturbing the parameters and choosing the perturbations that improve the value. So these are things like natural evolutionary strategies, CMAES, and so on. If you go from that to online actor-critic algorithms that do not use old data, that are fully on policy, like A3C, you will see about a 10x improvement in the number of samples that are required. And each step here is going to be about a 10x. Then you can have policy gradient methods, batch mode policy gradient methods. Then you have off-policy value-based methods, things like Q-learning, DDPG, etc. These are methods that use a replay buffer of data. Then you have model-based deep RL methods. And then you have shallow shallow model-based RL methods that do not use deep neural networks, but use some Bayesian function approximators like Gaussian processes. You can get about a 10x change in performance for each step along this column. So how am I going to prove this to you? Well, I'm going to look at a bunch of papers and I'm going to pull out results for tasks that look roughly similar. It's an imprecise art because not everyone tests on exactly the same problems, but insofar as possible, what I try to do is pull out results on a task that is identical to or very similar to the half-cheetah task, which seems to be a very popular one. So if you look at the half-cheetah task in this paper on evolutionary strategies, and you look at the half-cheetah task from A3C, you'll see a jump of about 10x. So it requires about 1 billion steps with natural evolutionary strategies and 100 million steps with A3C. If you look at results for trust region policy optimization, you'll see that it gets to decent performance after about 10 million steps or 10,000 episodes. So here, this is if the cheetah was running in real time, it would be 15 days here and 1.5 days here. Then once you go to off-policy algorithms, then you see actually a drop to about 1 million time steps, or the equivalent of about 3 hours of real time, which coincidentally is about as long as it takes to run some basic robotic manipulation tasks using these algorithms in the real world. So even though this is not half-cheetah, it's kind of nice to see that the numbers, at least up to an order of magnitude, roughly stack up. So we're looking at learning times of hours, so less than 10 hours, but more than 2 hours, let's say. Then if you go to model-based RL, then you see half-cheetah learning in the equivalent of 5 to 10 minutes. So there's about a 10x improvement there. And then there's some other papers that have analyzed head-to-head comparisons between model-based RL and things like DDPG. And there they also see about a 10x gap. So that's good evidence that the jump from off-policy model-free RL to model-based RL is somewhere about 10x. And then if you look at shallow RL, these are things like Pilco that use Gaussian processes. There you'll also see a 10x drop in the number of samples. Although, of course, you also see a big drop in the complexity of tasks that can be tackled because, of course, you can only use those methods for tasks where Gaussian processes are suitable function approximators. So this can maybe tell us a little bit about how sample complexity stacks up to different methods. But, of course, it's not the only factor that matters. And oftentimes, if we're concerned with computational complexity, meaning if you run in a simulator, your simulator is fast, and you have a big data center with lots of GPUs to use, then the amount of time it takes, the amount of wall clock time, will actually be almost inverted with the model-based methods typically using the most computation because they have to fit those complicated models and they have to update those models frequently. And the really simple things like CMAES and natural evolutionary strategies actually taking the least time because they can make ample use of parallelism and require very little actual computation beyond actually running those simulations. So the actual wall clock time, if you have unlimited parallel compute, tends to basically be inverted, with the most expensive methods being the model-based ones and the cheapest ones being the large-scale kind of on-policy online methods. Okay, so that's sort of the landscape of what sample complexity looks like today in reinforcement learning. But of course, you have to keep in mind that when I made this slide, I used the half-cheetah task, which is arguably the simplest continuous control task you can use for benchmarking. So what about more realistic tasks? Well, you actually pay a big cost for increases in dimensionality. So I said before that the half-cheetah requires about 10 million steps or 10,000 trials to learn a good policy with TRPO. If you go to a more complex task like a running humanoid in 3D, now you might require maybe, in this case, it's about 100 million steps. So you have a 10x increase in the number of samples that are required just because of the increase in the dimensionality. So the effect of underlying dimensionality, the complexity of the system. You pay a big cost for using images. So these were tasks that used a low-dimensional state. If you also had to learn directly from raw images, then that would also require substantially more samples. So even though we had this kind of rosy picture on the previous slide where we could use an off-policy RL algorithm and learn in the equivalent of about 3 hours, if we were to increase the dimensionality of the system by 10x and add raw images, maybe it would be 3 days instead of 3 hours. So we're not nearly there yet. And of course, you pay a really big cost in the presence of real-world diversity. So these are very simple tasks. The cheetah doesn't have to run in the woods. It doesn't have to run in the savannah. It has to run on an infinitely large flat plane with a checkerboard texture. So if you needed the cheetah to run in realistic settings, then there would be a lot of variety, which means that you would also need to train for longer in order for the RL policy to actually generalize to that variety. So if your setting is, like robots picking things up, and the things that they're picking up can be highly varied, then you might also need a much, much larger number of samples. So the problem with sample complexity in RL is very, very far from solved, and there's still a long way to go there. So what's wrong with sample complexity? Well, a very fundamental problem is that you need to wait for a long time for homework 3 to finish running, and then you might be late, or you might need to use a late day or something. But of course, this very academic challenge turns into a very practical real-world challenge once you try to apply what you learned in the class to realistic settings. So sometimes you want to solve a real-world problem, and there learning can become difficult or even just downright impractical, whereas over here it was merely inconvenient. So for real-world settings, if the sample complexity of your algorithm is simply too large to use directly on real-world systems, then you need to invest a lot of time into building good simulators. But then you're not out of the woods yet because your simulator also has to be really fast. And if you're simulating very complex phenomena, maybe it's actually very difficult to build a fast enough simulator to use some of these expensive algorithms. So in practice, very high sample complexity limits the applicability of reinforcement learning to real-world problems. And there's a lot that we can do to try to address this. We can work on things like model-based RL. We can work on off-policy RL. And so on. So there's a lot of room for improvement in this area in the world of deep reinforcement learning. So we can develop model-based RL algorithms. We can try to figure out what can it take to make model-based RL algorithms more general, more broadly applicable, more effective in your particular problem setting. We can design algorithms that are faster. And we covered, for example, a variety of different off-policy Q-learning algorithms, policy gradient algorithms, and so on. And those are by no means the last word on that topic. There are fundamental algorithmic improvements that can be made, and in fact, they continue to be made every year. So here I actually have 2 examples from 2018, 2 papers, one called Addressing Function Approximation Error in Actor-Critic Algorithms by Fujimoto et al., and another called Soft Actor-Critic by Harnoy et al. And both of these papers basically make fundamental improvements to off-policy RL algorithms that make those algorithms faster without really changing any assumptions, without sacrificing any of the generality. And there's a lot more to be done there. So just fundamental improvements to reinforcement learning algorithms. And then, of course, we can also get creative. We can look at things that are a little bit outside of the standard problem definition. We could, for example, look at algorithms that can effectively reuse prior knowledge. that introduces an additional assumption. It introduces the assumption maybe that you had other tasks in the past that you solved, and then you can use those tasks to gain knowledge to solve new tasks more quickly. And there's a lot of room for improvement there as well. And we learned a little bit about that when we talked about multitask learning and meta-learning. So there, again, there's a lot more to be done, and the current multitask learning and meta-learning methods, I would say, are still actually in their infancy. There's still a lot of work that can make them more practical and more broadly applicable. Okay, the third kind of core challenge, scaling and generalization. This is something that we don't really deal with very much in this course because for your homeworks you typically were asked to write reinforcement learning algorithms and apply them to relatively simple benchmark problems that you can run on your computer at home. But realistic problems can be much larger and much more varied. So usually when we think about machine learning, the big strength of machine learning is in its ability to generalize beyond what was seen in the training set. And many of the most impactful applications of machine learning make use of that property. So for example, in image classification, if you look at something like the ImageNet large-scale visual recognition challenge, it's a large-scale problem. It uses millions of real images harvested from the internet. It emphasizes diversity, and it's valued on generalization. No one ever asked, how accurately can your ImageNet trained model classify an image in the training set? No one really cares about that. What they care about is how accurately can you classify new images that were not in the training set. In reinforcement learning, typically the kind of problems that we work on, the kind of problems that we iterate on when we're developing algorithms are a lot simpler because we need some problems that are simple enough for us to get started. So they're relatively small-scale problems that emphasize mastery and are valued on their performance on the particular training setting. So if you want to answer the question, how well is your algorithm doing on the half cheetah? Well, the answer depends on how fast the half cheetah runs. It doesn't really depend conventionally on how many different terrains it can run on, for example. So there isn't a notion of a test error. But in many realistic reinforcement learning settings, there is such a notion. So if you want to train an actual robot to run on terrain, maybe what you care about, a lot more than how fast that robot can run, is what percentage of terrains that it will see in the real world will it successfully be able to run on. And that's a really big deal, and something that we often don't emphasize as much when we do core algorithms development. So where's the generalization? In a sense, when it comes to generalization, reinforcement learning actually has a big problem, especially the conventional view of reinforcement learning as an agent interacting with an environment in a loop. So to understand this problem, let's look kind of schematically at what supervised learning conventionally looks like. In supervised learning, there is also an environment. There is a state space and a kind of action space in a sense. You just don't touch it directly. In supervised learning, you have an environment, and somebody went out and gathered a bunch of data from that environment. Maybe somebody wrote a little crawler bot that goes to Flickr and pulls images from Flickr and uses the tags of those images, or maybe uses a mechanical Turk to label those images. That is part of the learning process. It's just not something that's exposed to your algorithm. Somebody else already did that for you. That's how the ImageNet data set was created, for example. But this is only done once. At that point, the data set sits there on your hard drive, and you can go and use that data set as many times as you like. So you can train for many, many epochs. You can train many different models. You can use the best model based on holdout error and so on. But remember that there was still a real physical process that went on to create that data, just like in reinforcement learning. However, somehow that data is packaged for you in a way that makes it convenient to train on that same data many, many times, improve your model and so on, and make real, meaningful research progress. And then when you're done, you can take your model and deploy it on your agent who can hopefully make useful decisions with it. In reinforcement learning, we have an active, an interactive learning modality where you have the environment, your agent interacts with that environment, uses that interaction to somehow improve their policy or model or Q function or whatever, and then typically goes and interacts with the world again to collect additional data. In fact, if you have an on-policy algorithm, which is kind of the extreme end of the spectrum for this, all of the data you collected the last time around is actually discarded when you go and update your policy. For off-policy algorithms, the data is typically not discarded, but you're still relying in a very strong way on collecting additional data to keep improving your behavior. So this is done many, many times. And of course, this is the textbook picture. The reality has an outer loop around this whole thing, and that outer loop is you. And that's you sitting there and improving your algorithm, maybe adjusting your hyperparameters. And this is also done many, many times, sometimes more than others. And this outer loop is not that bad if your algorithm runs in like a few hours or a few minutes in a simulator, but it can be really bad if this is, for example, an agent interacting with users on a website and it takes you a month to get one training run out of the way. So this can be also a really, really big deal, and then this guy might need like many cups of coffee in order to get through this, and it can make actual meaningful scientific progress very, very difficult. And how bad is it? Well, okay, so there's this, this video that I showed when I talked about policy gradients. This is a humanoid learning to run. It's pretty cool because the humanoid learns to run essentially forever. But this takes 6 days of real time if this was an actual humanoid running. And when it's done, it only learns to run on this infinitely large flat plane. So if the humanoid needed to run on like roads and hills and do parkour and like run on water and do all these different things, you know, the real world is not so simple. It would need to practice in all these different settings, but maybe more to the point, it would need to practice in all these different settings for every iteration of the algorithm. So imagine for a minute as a thought exercise, it's an impractical thought exercise, but it's worth thinking about. If this was a real robot, what do? You put it on a truck, you drive it to one place, you drive it to another place, you drive it to a third place, and you do this in a loop every single time you update your policy. Like that's just never going to work. It would be like, you know, training on ImageNet, except that now you have to take your camera and bring it to every single place every single time you update your network. So this is an impractical way to train in the presence of real-world diversity. And there are maybe a few things we can think about to try to remove this challenge. Maybe one of the things we can think about is, well, can we have sort of an extreme version of off-policy RL, where instead of still having this iterative process and merely retaining the data from the last time you went around, maybe you have something that looks more like the supervised learning setting, where somebody went and interacted with the world a whole bunch, collected a big data set, put that data set on a hard disk, used it to train many, many times, and then maybe occasionally went out into the world and collected a little bit more data just to fix up some issues with the policy, but mainly relied on that big prior data set for the generalization. So maybe this is where you were running on the hills, in the road, and doing the parkour, and maybe here you're just trying to figure out how exactly to place your foot in one particular, you know, obstacle course just to avoid any pathological issues with your policy. So we can go kind of on the extreme of policy end to try to address this generalization issue. There are other things we can do. We can, you know, try to set up the kind of frameworks that allow us to collect very large amounts of experience. We can look at, you know, model-based RL and other things of that nature. And this kind of stuff can make a huge difference in future work in realistic domains, where this kind of purely active, purely interactive cycle is impractical. Not just for robots, it can make a big difference for things like autonomous driving, where large amounts of prior data are readily accessible from human drivers, but interactive collection with an autonomous car, especially a partially trained autonomous car, can be disastrous. This can be a really big deal for things like language and dialogue. Wouldn't it be nice if we could use reinforcement learning to train an agent to talk to people? But of course, it's difficult to do that if every single iteration requires talking to millions of people, even if it's a chatbot, even if it's on the internet. But we have a lot of prior data of people talking to other people. Maybe that's something we can incorporate into the reinforcement learning process. And things like finance, inventory management, business operations, and so on, these are also areas that have lots of prior historical data that can be leveraged to improve generalization if only we had algorithms that could effectively make use of that. So can we get better generalization by leveraging off-policy data? That's one question we could ask. Perhaps model-based methods can help us there. Model-based learning might be a good option because the model, which is essentially like the physics of the world, it's task agnostic, so you can learn models from past experience where an agent was solving other tasks, or maybe not even solving any particular task, and then use that to help you solve a new task later down the line. And perhaps we can also think about what does it mean to have a feature of decision making. So in computer vision, we get great generalization from training on a data set like ImageNet because we learn good features. What's a feature of decision making? What is it? Perhaps a little primitive, a little mini behavior. We didn't talk about hierarchical RL very much in this course, but if you're interested in this question, this is a lot of what hierarchical RL deals with. So if you look up something called options, you'll learn about these primitives that you can acquire and generalize to new settings. So there are a few pointers to work on that. You could imagine little primitives that can be combined within a policy, things like in motor control, things like muscle synergies or low-dimensional spaces. So for people who study motor control in humans, for example, one thing that is often observed is that human behaviors, human motions, can actually be described as a superposition of a few bases. So even though you have a very large number of muscles, many of the motions that you execute actually can be modeled as a linear combination of a relatively small number of basis functions. And maybe that's one of the ways to think about features of decision-making and control. And there are many other ways that we can begin thinking about this, but this is still a very big open problem. We still don't really know what it means to have a generalizable feature of decision-making in the same way that we have features in computer vision or NLP or speech. Okay, so these are the core issues, the issues with the core algorithms. Next, what I'm going to talk about is another set of open challenges which have more to do with assumptions. Assumptions about what do we get in advance for our algorithm, what are we provided, and what are we expected to return at the end of the calculation. So this has to do essentially with the problem formulation. How should we formulate our decision-making problem so that it actually allows us to solve the tasks we want to solve, but also enables us to do so efficiently, in a stable way, and in a way that generalizes. So maybe at the risk of being a little inflammatory, what I can do is I can just show you side by side some problem formulations in ML. So here's the problem formulation for a supervised regression problem. You're given a data set D, which consists of tuples xi and yi, where yi is produced by applying an unknown function f to xi plus some noise. This is a very standard setup for a regression problem that many of you probably saw in a statistics or probability theory class. And then your goal is to learn a function f hat such that the expected error between f of x and f hat of x, this should be f hat of x, sorry, is low. So that's the goal in your regression problem. It's a very simple problem formulation. You can write it in 3 lines. Here's the problem formulation for reinforcement learning. Given a state S in script S, and A in script A, and an unknown dynamics P of S prime given S comma A, and an unknown reward function R of S comma A, and maybe like a discount factor gamma, and like a whole bunch of other stuff or something else, et cetera, et cetera, et cetera. At the end, there's something with produce a policy with high expected reward, but even that is something we can't always agree on because we have to decide how we're going to use the discount factor. So basically, when you want to write out this problem, just writing out the problem setting already takes much more space on my slide. And maybe that should be a hint that there's room for a little bit of flexibility. If the problem is very short to define like this, that's a very concrete, very concise problem. We can start making progress on it. If a problem takes a really long time to define, perhaps the really simple, really concrete set of assumptions, the most basic assumptions that we always have, isn't quite contained in here just yet. So maybe there's room to modify the assumptions a little bit, and perhaps in so doing, derive a new problem setting that is a better fit for the problems we actually want to solve, or perhaps provides us with the machinery to solve those problems more efficiently. So a few examples of things we could do. We could go in and say, okay, the reward function. Is it a known reward function? Like, can we evaluate R of S comma A for any S comma A? Or do we only see values from the reward function when we actually visit those states? Sometimes in RL, people refer to this as reward signal versus reward function. When someone says reward signal, what they mean is that there's a scalar value that sort of comes down from above that gives you the reward value at a state that you actually visit, but you cannot ask for the reward at a state that you did not yet visit. If someone says, I have the reward function, what they mean is they actually have this function R of S comma A, and you can ask that function for answers to any state in action, and that can perhaps let you build more efficient algorithms in some cases. The discount factor. Is the discount factor a property of the problem or a property of your algorithm? Do you actually want to solve a discounted reward problem, or are you just putting the discount factor in there because otherwise you get infinite sums and you don't like dealing with infinity? I don't know. Depends on your problem setting. So that's another assumption you can make. And there are many others. You know, sometimes the dynamics are unknown, sometimes they're known, and sometimes they're partly unknown. Maybe there's something about the dynamics you know and something that you don't know. Maybe your state space is structured in some way. Maybe you know about independence properties in your dynamics. Maybe some variables influence only some other variables, only a subset, but you don't know how they influence it. And that knowledge about independencies can also tell you something. So there is a lot of room for modifying these assumptions, and sometimes that can be very useful. So many assumptions equals many possibilities to vary the problem statement. Here are a few kind of bigger examples of variations on the problem statement. Single task or multitask learning. Conventionally, we think of reinforcement learning as a single task learning problem. There's a reward function, you want to maximize that reward function. But remember what I discussed before when I talked about running on the road and the hills, doing the parkour and so on. You could say that this is all one task, this is the task of running, or you could say that it's many tasks. And if you actually make use of the fact that it's many tasks, perhaps you can develop algorithms that are somewhat specialized to the multitask setting and therefore more efficient or more effective. So your generalization is going to come from the fact that there are many tasks, so it makes sense to kind of special case the fact that there's a multitask setting rather than a single task setting. You could, of course, always represent a multitask setting as an equivalent single task MDP. You could just say that it's an MDP with a stochastic initial state. So this is what we covered before when we talked about transfer learning. But perhaps if you actually make use of the fact that these are distinct MDPs, you can develop more efficient and more effective algorithms. And that's what we discussed a little bit in the multitask transfer setting. So even though this doesn't require any new assumption, it might merit additional treatment, and perhaps there's more progress that we can make in regard to algorithms that generalize effectively by taking advantage of multitask structure. So that could be a fruitful area of future investigation. So you could train on multiple tasks and then try to generalize or fine-tune. We saw this for things like policy distillation, actor-mimic, meta-learning algorithms, and so on. And you could also imagine saying that, well, maybe you have a multitask setting where you have either no supervision, meaning no reward function, or you have kind of weakly supervised tasks. And we saw a little bit of that when we actually talked about the control via inference, when we saw fine-tuning from the quadruped running in different directions to running in a single direction. And there's been a bit of research on kind of similar sets of assumptions where you have a multitask setting, but the multiple tasks have weak supervision, have reward functions that are not very informative, and they're really meant to be there to allow your agent to practice different skills so they can then generalize to new, more narrowly defined tasks. And of course, there are many other works in this area. So building off of that point, one question that we might ask in reinforcement learning is, where does the supervision come from? So if you want to learn from many, many different tasks in order to generalize, you need to actually get those tasks from somewhere. Someone needs to tell you what are the different things that you can practice so that you can generalize effectively. If you have Atari games, very easy to figure out what you need to do. You need to maximize the score. But in real-world tasks, maybe it's not obvious what you need to do. And maybe it actually takes a lot of effort for someone to program in what are the goals of different tasks, which is maybe okay if that's a task they really want to solve. But if you want multiple tasks to practice in order to generalize, it can be very onerous to program in the reward functions for all those different tasks. So maybe one modification we might want to make to our assumptions is that maybe the reward is not known. Maybe it has to be inferred from other kinds of data like demonstrations. Or maybe it's not known and you're not going to get any demonstrations. You just need to figure out on your own what is interesting to do. So perhaps you can generate objectives automatically. That's a change to your assumptions that on the surface might make things harder, but in practice it might make things easier because it allows you to practice in many more different domains where you might not have a reward function, and from that generalize better. So what's the role of a reward function? What's the reward function really doing? And conventionally, we had this view that the reward function specifies what you want your algorithm to do. It specifies the what, but not the how. But we also saw that in practice, this is not really how reward functions always work. So if you have this little walking robot, we saw this in the very beginning of the course when we first talked about reward functions. You might imagine that you specify a reward function that is like 1 if the thing is walking and 0 if it's not walking. That makes sense. Like, I want it to walk, I'm going to give it a 1 if it does it and 0 otherwise. But in reality, if you want this thing to walk, with most current reinforcement learning algorithms, you would need to provide a reward function that looks more like this. W1 times its walking velocity plus W2 times whether the torso is upright plus W3 times whether the height of the root is above some point, and so on and so on. Simply because this reward signal is too uninformative to acquire a policy entirely from scratch. So a more informative signal provides a more smooth, more well-conditioned energy landscape for your reinforcement learning algorithm to climb in order to find a good policy. So this kind of makes us question whether the reward function is really there just to define what the task is, or is it really there to partly define how to do that task? And this is, it's kind of tempting to look at this and say, well, it's just because our algorithms aren't good enough. Like, just wait another couple of years, they'll be good enough, and we'll be able to do this. But the fact is that, even for humans and animals, who are probably much more intelligent than the algorithm that's trying to make this guy walk, the reward function is really complicated. There's a part of your brain, the basal ganglia, which is widely considered to be the bit that's actually responsible for the reward signal insofar as you have one. And it's like it's a big part. Like, look at that thing. Like it takes up quite a bit of space. There's quite a few neurons in there. So it must be doing something. And in fact, if you work through a little thought exercise, it actually becomes pretty clear that reward functions that just tell you what to do are probably not sufficient. They have to tell you a little bit about how to do it. Imagine that you're a predator and you have to chase down this gazelle. You really have to succeed at this task, because if you're unable to chase down the gazelle, then you will not have enough food to eat. So it's a very important task for you to solve. So if this predator is relying entirely on a reward signal like this to learn how to hunt the gazelle, what it's essentially doing is it's going to be kind of running around randomly, maybe biting at different things, until it just happens to eat a gazelle by accident, feels a very strong sense of fulfillment, and then learns to hunt down gazelles in the future. That's very unlikely to work. And we don't see animals doing that in the wild. So it seems like one way or another there's a more informative supervision signal at play. Yes?
So can the agent cheat according to the reward, cheating?
Say that again?
I think the agent can cheating in the reward according to you define the reward function. Whereas if you want to go faster and faster, he may do something weird like this.
Right. Yeah. Well, yes. So that is actually a very important kind of flip side to this thing, is that, and this is for those of you that didn't hear, like maybe the agent can cheat against the reward function, can exploit the reward function in some way, and that absolutely happens. And you kind of get you have this problem where you need to strike a balance. If you have a reward function like this that tells you exactly what the what without any of the details about the how, in some sense you can be confident that if you've maximized that reward successfully, then you're doing the right thing. If your reward function is more like this, there's a whole bunch of little details there. Yes, it will help you learn the task more quickly and more effectively, but you might end up solving the wrong task. Perhaps there's a way to exploit that reward function and do something that makes that reward value big, but doesn't actually do the thing that the user wanted you to do. And therefore you have to strike this balance. You have to tell the agent just enough to solve the problem, but not so much that your flawed human intuition causes it to potentially do the wrong thing. You have to kind of avoid the genie issue. The genie gives you 3 wishes, but the way the genie fulfills those wishes is not necessarily the way that you had anticipated them to be fulfilled. Okay, so what can we think about as potential solutions? Well, we could think about being really clever about designing reward functions, or even learning reward functions from demonstrations. But you can also imagine having agents that can learn from other sources of supervision. One of the things you could imagine is maybe agents that can learn something about the world, even in the absence of a reward signal. Maybe the cheetah can learn something useful that it can later utilize to hunt down the gazelle without having actually eaten any gazelles yet. Maybe it can learn to run, for example. So you can interact with the world even without a reward function, and that can give you useful knowledge. You can learn something about the world from that interaction, and there are a variety of choices about what you could learn. And then you can use that knowledge to solve new tasks quickly. And of course, there are also some choices to be made here about how you actually use that knowledge. We saw a few examples of this in the class. So we saw in the meta-learning lecture some discussion of this thing that Chelsea called unsupervised meta-learning, where the idea was that you have automatic task proposals. Here are some examples of automatic task proposals for the cheetah. In this case, these task proposals are constructed by incentivizing the cheetah to discover tasks that are easily to distinguish from one another. So if you look at this thing and you look at this thing, you say, okay, these are clearly 2 different things. That's not by any means the only way to do it, but it's one example. And then you can use this kind of unsupervised knowledge to do something that will help you solve new tasks more quickly. So in Chelsea's lecture, she talked about how that can be used to do meta-learning. You can also do other things. You can use it to learn primitives for hierarchical reinforcement learning. You can use it to learn models, whatever. So there are different ways to acquire the knowledge, different ways to use the knowledge. Question in the back.
So the problem that we're trying to solve here, as I see it, is this sort of 1-0 kind of loss that is basically, it doesn't create a good policy. So we're talking about how we need to learn our own sort of rewards. But that seems to be still in the context of that particular task. So if you're to generalize to humans, for instance, and you're playing something like chess, there is a 1-0 reward that probably doesn't generate a good policy on its own, but the human learns its own reward. But that's not just a random reward, that's a reward in the context of a task.
Yeah.
What we seem to be discussing here is more randomized rewards, but of the context of any task whatsoever.
So this is a very good point. For those of you that didn't hear, basically the point is that you could basically use your experience to construct some kind of knowledge that is specific to a task, or you could use your experience to construct some knowledge that is agnostic to tasks. And I think there's a lot of room for very fundamental improvements to our algorithms in both camps. So there's a big advantage to acquiring knowledge that is agnostic of task, because then you can use it for many different tasks. So if it takes you 10 years to acquire some knowledge, but you can use that knowledge for everything you want to do later on, maybe it's worth the time. On the other hand, if you're acquiring knowledge that's specific to a task, perhaps you can do a much better job. Perhaps you can really specialize and do a really awesome job at like playing chess, for example, if you don't have to worry about learning things that are useful for like playing checkers. And I think there's a lot to do in both areas. There was a question here?
So you supervise here, unsupervised here means without a reward function.
Yes.
So how can you then?
Right. So the kind of two parts here. First, unsupervised means without a reward function. I think generally unsupervised means without knowledge from a person. So if you say that the reward function comes from a person, that's the supervision. How can you learn something without the reward function? Well, you can learn things about how the world works. And essentially, these kinds of things, they can be viewed as knowledge about how the world works. So the fact that you can do a backflip, that is a property of the world, regardless of which task you're solving. Perhaps that property is useful to you, perhaps it isn't, but it's something that you can, it's like a true fact that you can remember and make use of later down the line. And that's basically the most that you can do in the absence of a reward signal. There's only really two parts to the setup. There's the environment, and then there's the reward. So you either learn about the environment, or you learn about the reward, or about both. And if the reward isn't there, the only thing you can do is learn about the environment. Any other questions?
So this is done by intrinsic reward?
Yes, so when you hear something like intrinsic motivation or intrinsic reward, that's basically referring to things like this. Yeah. And the particular way that you design that, of course, there's many different choices. This particular intrinsic reward is based on a discriminability objective. Okay, other sources of supervision, other than making up your own tasks. You could, of course, look at demonstrations, and that's a very powerful source of supervision, especially if you can mine demonstrations from watching people do things. And there's, of course, been quite a lot of work, especially in areas like robotics, where you can use demonstrations both to specify the goal of the task and to specify how the task should be performed without having to manually engineer reward functions. You can look at modalities that people use naturally that can be used to figure out potential things that an agent could try to do, potential activities, or potential ways to even represent the world. So language, for example, carries a lot of knowledge, not just for the purpose of communication, but also about how the world is structured. Right? The reason that we structure our language in a particular way is because that's the right structure for describing our world, which means the structure of language reflects the structure of the world in a very meaningful way. There's been quite a lot of work at the intersection of language and reinforcement learning that studied these kinds of questions. I want to briefly mention this one. This is a paper by Jacob Andreas, who was actually a student here at UC Berkeley, called Learning with Latent Language. And the idea in this paper was, can we structure the agent's representation of the world in a more meaningful way by giving it language during training? So the goal was not to build an agent that can listen to language and perform the task that's described in the language. It's actually just to use the language to structure its understanding of the world. So the setup here was that the agent was actually provided with natural language descriptions of tasks during training. So you saw a bunch of different tasks. The tasks all kind of look like this. This is actually an environment that was designed in, I believe, the Barzilay lab at MIT that Jacob used. And they all involve like going to a particular object in a little 2D world. And then the language descriptions would be like, go to the red star or something like that, go to the blue horse. Now, the structure of these commands actually reflects something about the world. For example, it tells the agent that grass and water doesn't really matter, but objects like horses and stars do matter. Now, if you train a policy like this, internally, it'll learn based on the language to go to different objects, and it will not go to like water or grass because those were not salient during training. So in this particular paper, what Jacob did is he set things up so that when there's a new task that's observed later on, a new task that's observed without a language description, instead of exploring randomly, what the agent can do is actually generate new strings, literally think of new sentences in English, and then execute those things. So it's kind of thinking out loud. It's saying, well, okay, I don't know what I'm supposed to do. Maybe I should go to horse. Maybe I should go to star. Maybe I should go to rock or something. Because those are the types, those are from the distribution of things that I saw during training. So that's an example of how language can structure the agent's understanding of the world. Another really interesting idea for a source of supervision. Perhaps demonstrations are hard to get because demonstrations require a person to actually do something. But perhaps in lieu of demonstrations, what you can get is preferences. You can get an agent that does something and then asks a person, do you prefer me doing this or do you prefer me doing this other thing? Maybe your robot in your home will go do the dishes, it'll break the dishes, and then it'll wash the dishes. It'll say, do you prefer me breaking the dishes or washing the dishes? Which one is better? It's the optometrist algorithm, A or B. And it turns out that if you set this up right, this is from a paper by Paul Cristiano, you can actually get agents in these kind of Mujoko simulator environments to do some interesting things. So it might be a little hard to tell. I unfortunately couldn't find a video of this, but what this is showing is the Hopper robot that you saw in homework 1 doing a backflip. So what it does is it jumps up and then flips over and lands. I don't really know how to design a reward function for the Hopper to do a backflip, but the way that these guys generated this behavior was by having the Hopper act randomly and then ask the person whether they prefer A or B. Then the Hopper adjusts its behavior based on this preference, tries again with some injected noise, and again asks, do you prefer A or B? And if you go through this iterative cycle many times, a few hundred times in this case, then a person can actually teach the Hopper to do a flip only by providing preferences, A or B. So that's an interesting source of supervision. You can think of many other sources of supervision. You can think of demonstrations in a different context, descriptions, maybe an agent is interacting with people in their natural environment and listening for sentiment in the words that they speak. There are many, many other sources of supervision that you can imagine leveraging for an agent to learn about what are useful things to do in the environment or what are things that it can learn about to be more useful later on. So we also have to, of course, grapple with this question of whether the supervision should tell us what to do or how to do it. And in all of these cases, that question is kind of a little bit confounded. So you might argue that the demonstration is showing the agent what to do. It needs to hit the tennis ball, but it's also giving it a lot of knowledge about how to do it. The language, it's literally telling it what to do, but contained in that instruction is also a lot of knowledge about how to do it. And of course, the preferences, they're also meant to elicit what is the goal of the task, but in the process, they inevitably elicit something about how that task should be performed because of the structure of the preferences. So the kind of things that we might think about as we rethink the problem formulation, we might say, well, how do we define the control problem? What are the things that we assume we have in advance? What are the things that we don't have? And what are the things that we need to produce at the end? What is our data? Is the data experience, our own experience, someone else's experience? Is the data annotated in some way with rewards, with language, with preferences, and so on? What is the goal? Is the goal to something fairly simple, like run or not run? And what is the supervision, which may be distinct from the goal? So maybe the goal is to make the guy run, but the supervision is something like W1 plus speed plus W2 plus torso angle, etc. So it may not be the same as the goal. Think about the assumptions that fit your problem setting. So maybe in your particular problem setting, there's a set of assumptions that are a little different from the standard reinforcement learning assumptions, but that actually make it much easier to learn efficiently and to acquire good policies. And that's something to take advantage of. And don't assume that the basic RL problem is set in stone. There are many somewhat idiosyncratic choices in the standard problem formulation and many modifications that you can make in your problem formulation. All right, in the last little bit of today's lecture, what I want to do is I want to come back to the bigger picture, something that we touched on in the very first lecture of the course. So in the very first lecture of the course, we talked about learning as a basis for intelligence. And one of the things that we mentioned is that it makes a lot of sense to think about deep reinforcement learning in this context because reinforcement learning, that's what allows us to reason about decision making. Deep models are what allow RL algorithms to learn and represent complex input-output mappings. So deep models are what can allow reinforcement learning algorithms to solve complex problems end to end. And we talked in the first lecture about how this might be really important to develop intelligent and adaptive agents that can solve any problem that you want them to solve. So here I think it might be worthwhile to, for a reminder about what is kind of easy and what is hard in this domain. Deep learning in RL can solve some problems really well. For example, it can achieve a high degree of proficiency in domains that are governed by simple and known rules like chess, Go, and Atari games. It can learn simple skills with raw sensory input given enough experience, like basic robotic manipulation tasks. And it can learn from imitating enough human-provided expert behavior. And we saw some examples, for example, in autonomous driving where this could work really well back when we talked about behavior cloning. But there are also some things that are very challenging for deep RL algorithms that are not so challenging for humans and animals. And that we can also look at that for ideas about where there is a big gap for improvement. So humans can learn very, very quickly. From just a few trials, they can adapt to new situations, to new perturbations for motor control skills, and so on. And deep RL methods are usually slow. Humans can reuse past knowledge really, really well. Transfer learning is something we talked about, but it's still a big open problem, and there are a lot of different competing approaches, and it's not clear which one is best, or even if any of them are best. And it's not clear what the reward function should be, because the speed with which humans adapt clearly suggests that there is a kind of a more informative source of supervision in there. It's also not clear what the role of prediction should be. Should we think about learning skills in a trial and error way, or should we think about learning how to predict and then using those predictive models to act, or maybe a little bit of both? And we might wonder at this point, well, what is really missing? This is a slide that I borrowed from Professor Jan LeCun, and I think this slide actually illustrates in a very interesting and quite clear way one of the things that might be missing in terms of a very kind of information theoretic view of learning. So let me explain this a little bit. In this slide, what Jan LeCun argues is that pure reinforcement learning, learning from rewards, is a very inefficient way to learn because there's so little knowledge that is gained from every single sample. So in an information theoretic way, if your agent needs to learn something that requires n bits to represent, then it needs at least that many bits of supervision. Like whatever it gets in that big deep net through gradients, all of that signal has to originate at the supervision. So if you're doing, for example, supervised learning, you're learning about the labels. So you see a bunch of these images, but just images by themselves don't tell you anything until you get labels. So in a sense, the information you get from every sample is the number of bits that are needed to represent that label. So then typically the number of bits that you get is 10 to 10,000 bits per sample, depending on how richly your space is labeled. So if you're just doing one of n categories, then it's log n bits. If you're doing semantic segmentation, maybe there's a few more bits. So there's kind of a medium amount of information in supervised learning. In reinforcement learning, arguably, there's less information because the reward function is not very informative. It's something simple, and even though you're interacting with this complex dynamics, maybe all you're really getting is that the log n, where n is the number of bits you need for the reward. So what he does in this slide is he argues that maybe what we should really think about is augmenting all of this stuff with unsupervised or predictive learning, because if you're learning how to predict the future, then the number of bits of supervision you're getting is the number of bits you need to represent your observation space, which is much larger. So if you learn to predict the next thing that will happen to the hopper, that's a lot more bits than if you're just learning to predict the reward function of the hopper, which is what a Q function learns. So this is kind of a very information theoretic view of learning, and it says that, well, really if we want learning to be efficient, meaning that we want to solve complex problems where the solution requires a lot of information, then we really need to augment our learning with unsupervised learning or prediction, right here. But of course, that's not the only view of this. I think it's nice because it helps to kind of illuminate this idea that what's missing is a rich source of knowledge. And then the question is, well, where does this rich source of knowledge come from? So one place that it can come from is unsupervised learning or prediction. So it can come from basically Jan LeCun's cake, that unsupervised or self-supervised learning is sort of the bulk of the cake, and then the little bit of supervision that you get from the reward is the cherry on top of the cake, but a very important cherry. So if we subscribe to this view, then we might say, well, we really need to understand model learning, prediction, unsupervised learning, and so on. Maybe we need to think about generative models a lot more seriously in the context of RL. This is nice because it gives you a lot to do before you even accomplish the goal. Before the cheetah even eats the gazelle, it can learn how to predict how the gazelle will move, how its legs will move, and so on and so on. This is a lot of knowledge to gain. But there are other ideas about where you can get rich sources of knowledge, and these are not by any means mutually exclusive, but they're worth considering. One view that you might consider, which I'm not sure if this is the right view, but it's an idea, maybe imitation is actually not just a nice thing to have, maybe it's actually a fundamental thing to have. You can argue that people and animals are very intelligent, but across the board it seems like the animals that are the most intelligent, at least in the sense that we in the kind of definition of intelligence that we find the most intuitive, they're often also the ones that are the most social, that interact the most with other animals, typically other animals of their own species. And perhaps there's something to that. Perhaps intelligence, even though it takes a lot of adaptability and flexibility on the part of the individual agent, is, at least to some degree, a collective phenomena. And the kind of intelligence that we find most impressive actually emerges through the interaction of many agents. So we're social animals, we have a culture, and maybe that's for a reason. And perhaps that is where some of that cake actually comes from. Another idea is that, well, maybe it really is just reinforcement learning. Perhaps it really is about the giant value backup. Perhaps even though the reward function gives you just a little bit of information, that information is modulated by a very rich interaction with the environment. And that interaction, in a sense, augments the amount of information in the supervision. So even though you get just a reward of +1 when you eat the gazelle, the complex pattern of interaction that led up to that event actually tells you a lot about what you should be doing in new situations. And maybe the fact that the supervision is sparse is actually just an illusion. In fact, it's dense because it's the reward plus the environment that are interacting together. And maybe there is, in fact, enough to learn if only we can develop a better reinforcement learning algorithm. So this is maybe kind of the reinforcement learning fundamentalist view, but worth considering. And maybe it's a little bit of all of the above. Maybe it is about augmenting with unsupervised learning and prediction, making use of social interactions, and also developing better reinforcement learning algorithms that can make the most out of the supervision that we do get. So how should we go about answering these questions? Well, one important point to keep in mind is that we have to pick the right problems. So we experiment a lot with little simple tasks like OpenAI gym tasks. We did this for imitation learning, for homework 2, etc. But perhaps to make real progress, we need to look at more complex tasks. Perhaps we need to look at tasks that have the kind of diversity and complexity of, let's say, the ImageNet data set, only with interaction. Well, what would be the equivalent of ImageNet in terms of complexity that actually implicates decision-making and control? Maybe we can think about that. Maybe we can look at tasks in the real world, tasks that involve actual physical agents, not necessarily just robots, but also, for example, real agents on the internet interacting with real people, or other settings where you have kind of where the full brunt of real-world diversity and complexity is inescapable. Another thing that I would suggest is maybe to make sure to pay attention to other areas that are not just reinforcement learning, but it can actually help us solve that challenge of where all the supervision comes from. Things like generative modeling and prediction, but also things that might deal with the imitation and the demonstration aspect, things that involve modeling other agents. And also more generally, just to carefully understand the relationship between reinforcement learning and other fields in machine learning, because some progress will come from developing better core algorithms, but some progress will come from bringing in ideas from other related fields that will allow us to make progress in new ways. Okay, well, that's it for today's lecture. We'll resume next week with guest lectures, so I highly encourage all of you to come. And remember that on Wednesday we'll have a talk from Craig Boutillier, who will talk about reinforcement learning, probably for things like recommender systems and theory. All right, I'll see you all next week.